Oh, well, thank you very much, Joseph, for this very kind invitation. It's a great honour to be here, and thank you for your kind words. I've known Joseph since about 2002 in the Australian conference in Melbourne, and I've learnt a lot from him. And I think we complement each other in some ways, because I have been fortunate enough to have access to high-tech equipment, a lot of electron microscopy, state-of-the-art synchrotron and high-tech equipment. So we spent a lot of time just understanding geopolymers from the basic science, material science point of view. But Joseph has a lot of insight and intuition, and most of the time he's right. Usually we find it 10 or 20 years later that he was right, you know. So I'm very glad to be here, because there's a lot to learn, and I think you're fortunate to be here too. So I'd like to talk about the geopolymer route to high-tech ceramics. And this work has been supported over the last 18-20 years by the Air Force Office of Scientific Research, Dow Chemical Company, the Army Research Office in Aberdeen, and the US Army Corps of Engineers more recently. They have a construction engineering research lab in Champaign, Illinois, and they're quite interested in applications. And over the years, there's been generations of masters, PhDs and postdocs that have contributed to this geopolymer work. And today's talk, I've only got 30 minutes, so I'll get to the point. I would like to talk about composition and starting materials, microstructure, processing routes to ceramics, especially oxides and non-oxides. And I've recently been asked to write a review paper for this set of books published at Oxford about comprehensive composite materials 2, and this is a contribution to volume 5 of those books. So yes, you already know this, but when I give this talk, it's always Joseph Davidovich that introduced the term geopolymer. When I first started, I was confused, because I ended up going to Kiev to visiting Pavel Krivenko and Viktor Glukovsky's lab in Kiev, and I always couldn't understand. Are they talking about geopolymers? Joseph's talking about geopolymers. Who invented it first? And after a lot of confusion, I've decided that Joseph invented it first, and the Kiev people, are really talking about alkali activated cements. So for us, over the years, this is what geopolymers means to us. The chemical word is polysilicate aluminate, polysilates. They're a type of chemically bonded ceramics of the formula 1 group, 1 oxide, 1 alumina, 4 silica and 11 water. That 11 water is just an arbitrary number. It depends on the specific surface area and particle size of the powders. We use BASF, but I'm learning there's a whole bunch more even varied sources of metakaolin. It produces a refractory. They're refractory inorganic polymers formed from aluminum silicon tetrahedra under highly caustic conditions. They are a rigid, hydrated aluminosilicate solid containing group 1 charge balancing cations. They result in an amorphous, nanoparticulate, nanoporous, impervious, acid-resistant polymeric structure. And there's metastable zeolites. That's in the case of sodium-based geopolymer, it's a metastable zeolite, or maybe sodalite. I learnt a lot of my stuff from Ken McKenzie in New Zealand, and we sort of cross-fertilised each other, and then, I'm getting more and more knowledge by hanging around with Joseph and his team. So the way I see it, as a physical and inorganic chemist, if you have 5 molecules of silica, the oxidation state's +4. If you take away 1 mole, you get back with 4 moles of silica +4, and you replace that silica with 1 mole of alumina, that's +3. So you need another +1 to make +4 to get back to here. So this is a group 1 oxide, sodium, potassium, lithium, cesium, rubidium, franconium, and the water, just for the rheology. You need water. So the way to make it as a material science model system, to keep it simple, is get clay. And when you heat clay, it'll become metakaolin, and it'll be like a ceramic engineer writes. That's what I teach at Illinois. 1 mole of alumina and 2 moles of silica, and the water's gone. You know, if you heat it to 750 C for 1 hour. But the other ingredients come as you take, say, sodium hydroxide, potassium hydroxide, cesium hydroxide, and you dissolve in 2 moles of amorphous silica. And that could be from, various silica, Cabosil in Illinois, we got Tuscola, Cabosil, or ground up glass, so long as it's amorphous silica. It can't attack anything that's crystalline. It's not strong enough. And so that makes a solution, and that's water glass or sodium metasilicate, and that's the clay. Now, yes, the big long-winded confusion about alkali-activated cements, it's even more clear to me now after Joseph's talk this morning. This is the ternary phase diagram: silica, group 1 oxide, and alumina. 114. The reason we say 114 is because 18 years ago, I realised people didn't really know what they were talking about in terms of what is a geopolymer, so I put it in the TEM, and I did EDS, chemistry, on it. And I always found that the characteristic microstructure had a characteristic chemistry: 114, 1 alumina, 1 group 1 oxide, and 4 silica. And that's this. So that's what I call a geopolymer. It's a stoichiometric geopolymer, and that's because that's what I see in the TEM all the time. Not the overall mixture I started with, but geopolymer's got a characteristic microstructure. Then I was on PhD exams in civil engineering, and they were supposed to be doing geopolymers, and I sit there halfway through the exam, all right, when are you going to start talking about geopolymers? And the civil engineers think they're talking about geopolymers, but they're really talking about things over here, and they're selling themselves short in terms of the mechanical properties. Cash and Nash, no. Well, even you shouldn't be saying Cash and Nash anymore, but that stuff is definitely not geopolymers, you know. So anyway, so geopolymers are a potential partial solution to global warming. 1 tonne of Portland cement liberates 1 tonne of CO2, but to make 1 tonne of geopolymers, you only liberate about 1/4 of a tonne of CO2. And the mechanical properties between ordinary Portland cement and geopolymer composites are geopolymers roughly twice the strength of cements in compression, 3 times the strength in flexure, half the density, and set to full in 1 day. So it's the synthesis. So here's a different list over the years. It started maybe with Victor Glukovsky and slag in the USSR, making the alkali-activated cements. A lot of fly ash from coal plants in Australia. Joseph, 18 years ago, gave me the tip of starting with the clays. But in New Zealand, Ken McKenzie uses halloysite. And then I've talked to various people. You could also use the black glass from plasma incinerated, you know, rubbish. Every week somebody comes and takes your rubbish away and burns it, and then that leaves a black glass, and you can make geopolymer out of that as a silicate source. Recycled glass, cull it, grind it up. Basalt from organic tuffs can be made into on Hawaii, all those volcanoes, on Mars, there's a lot of basalt. So NASA's, realises this. And meanwhile, there's a whole bunch of biological materials, rice husks, bamboo leaves, elephant grass, 50% silica, 80 to 90% silica by calcining these products. So the Army's interested for using indigenous materials. Wherever you are, use what you got. Don't wait for it to come in the mail. Okay, so this is my version, what Joseph told me 18 years ago. Kaolinite is crystalline and the aluminum's in six-fold coordination. When you make it amorphous by heating, it goes into five-fold coordination. And this is a highly strained molecule. How come that you can make a ceramic material which usually you have to fire it to 1,000, 1,200, 1,300, a long time, long energy, and here just water can make a ceramic material? It's because when it's amorphous, the concentrated NaOH or KOH can attack this molecule, and it's so strained in this five-fold coordination that it is attackable, and it can be broken up into the tetrahedra, AlO4-, and away she goes. So that's the critical step. Terry Trigg, Australia, CSIRO, Melbourne, the rate determining step is the dissolution of the aluminosilicate source. And this is it. And so crystalline aluminosilicate's no good for making geopolymers. It's got to be this strained molecule. And the same principle might apply for other chemistries, the phosphates. So anyway, you get a powder and a liquid. A high shear it, that's the other trick. The first year, we used a milkshake mixer with a little propeller, and we had a lot of unreacted phase, only 50% reacted. And then with a high shear mixing paddle with teeth up, teeth down, teeth up, teeth down, and we use this. And that makes the rheology good. First, you get the powder and the liquid, and you get texture of toothpaste. But when you put it in a high shear mixer, it becomes low viscosity, like honey in summer, runny honey. So that's the trick. As soon as you attack the metakaolin, you have to clean off what you've formed so keep the reaction going. You need the high shear mixer. And then you put it into a mould and it doesn't stick to plastics. And then if you wanted to, you could heat it to 50 C and you'll get it in 12 hours. But I don't know the property's quite as good as the room temperature. You can put nice colours in like this, and you can have a nice mould. And there's always the water tries to get out, so that it makes a film at the interface, and you can demold it readily. This is from since 18 years now. I've been organising the international focus session on geopolymers at part of the American Ceramic Society. I try to make a home for geopolymers in ceramics, and they let me do it. And now they want to make it a symposium, so next year it's going to be a symposium. But this was Ho Chi Minh City, PhD student from North Vietnam came, and you can put beautiful colours in, and you can make a souvenir. It looks like bronze, but it's not. So, microstructure. All right, now we all know it's SiO4 and AlO4 tetrahedra. More practically in the lab, when you make a metakaolin, you get an amorphous hump at 22 degrees 2 theta. When you make geopolymer, it migrates to 28 degrees 2 theta, 30 degrees. You might have impurities. This is BASF with some titanium impurities. But if they're crystalline, the geopolymer can't touch it. And now this Ken McKenzie current version of what the atomic structure is. SiO4 tetrahedra, AlO4 minus tetrahedra, like a glass, but it's never been fired. But AlO4 minus needs a charge balancing cation to hang around. And that charge balancing cation is surrounded by water of solvation. So this is the current material science accepted version of what a geopolymer is. And in the SEM, it's nanoparticulate and nanoporous. So they look like cauliflower to me, you know, a pretty weird structure. I mean, I teach TEM. I never saw such a crazy structure. And then in the TEM, well, if you just make it by crushing it and dispersing it on a grid, you get little nanoprecipitates. Little precipitates like pancakes that fall out. And if you use sodium or potassium or cesium, they got texture, a little black and white, you know, I don't know, but it's beyond the limit of TEM by now. And there's texture inside a texture inside a texture, and this is sodium, potassium, cesium. Maybe sodium's like 20, 30 nanometers, 30, you know, 30, 40, 40 nanometer splats, these little splats and precipitates that stick to each other. And then a high angle annular dark field, it's nanoprecipitates. You can see those little pancakes just sitting on top of each other, but it makes a tight, coherent structure. And then if you send it out for pore size analysis, porosity measurements, so by Porotech, with potassium, the average pore radius is 3.4 nanometers, but it's 41% porosity by volume. And potassium is pretty homogeneous porosity. Sodium is a bit heterogeneous. The mechanical properties of potassium better than sodium. If you make geopolymer by a synthetic method, which is organic steric entrapment that we have a patent on in the US, you can get average pore size 0.8 nanometers, or a radius, which is 1.6 nanometers diameter. So 6.8 nanometers diameter porosity, 41%. And now porosity in geopolymers, right, people might be interested in using that for something. So if we add peroxide to it, you can get 45% pores in there. Don Sayo at Arizona State invented and got a patent on putting in cooking oil, canola cooking oil, and produced with sodium saponification, soap making, and he can make hundreds of microns pore sizes. And then he just washes the soap out, and it leaves a porous geopolymer. Other people have put in bentonite or kitty litter. That makes porosity like bread. We did a PhD with support from Dow Chemical. They wanted zero gels or aerogels. So we worked with alkoxysilanes, and we could make 75% volume porosity, 1 micron pore size. You could also just put in lots of water, but that's just like a porous material. It's got low strength. Here is this is what we did with Dow Chemical, the silane. So you can have 1 micron pore size and 75% porosity. That's published. So, well, meanwhile, moving on to the structure, we see as black and white in the TEM, and then we reach the limit of high resolution TEM. So we switch to radial distribution function in glass, or in the synchrotron work, it's paired distribution function, PDF. And that means you have one atom, and it measures the distances to all the other atoms in the material and what types of distances are there. It's an amorphous technique, and Basically you get, this is the distance between the other atoms, like a histogram of characteristic distances with all the other atoms, and you get this function in real space which you get and then it makes a histogram, and basically it says that even at room temperature you've got characteristic units of tetrahedra, AlO4 minus and SiO4 tetrahedra, and in the case of cesium as a charge balancing cation, you can get it out to about 7 nanometers, 7 angstroms, and you got these tetrahedra building blocks already in place, but they have no long range order. So you got polymers, but there's snakes in a box going everywhere, and you want them, if you want to crystallize them, they're all supposed to lie down straight. So if you want to crystallize like this material, which is called pollucite, you have to heat to 1000 C. So this real geopolymer is stable to 1000, and then the worst thing it can do is crystallize, and then pollucite melts at 1940 C. So that's, that might be useful like for radioactive cleanups. Now if you take that PDF function and you subtract the room temperature from the higher temperatures, there's no difference in the types of units, the SiO4 tetrahedra, the AlO4 minus tetrahedra. The only difference is around about 1000 it crystallizes. The other thing is this sodalite, zeolite formation. It's a metastable zeolite. That's what the Australians told me. If you give it a lot of water, then the molecules can swim around and start making nice crystals. But if you didn't give it enough water, then it makes a geopolymer structure. And also the chemistry has to be right. Only sodium can make zeolites, that it's 1, 1 soda, 1 alumina, 2 silica. Then you make zeolite. You could, little nanocrystallites, but if it's 3 silica or 4 silica, you don't make zeolites. So only in the case of 1,1,2 composition for sodium can you make zeolites. And so here's a picture of the zeolite. If you add more water, it doesn't change the atomic structure, but it changes the microstructure, makes it more porous. Now, this is a bit of a problem. If you're in structural ceramics, you want to make some useful structure out of it. Well, it's good at room temperature, so long as you keep it at room temperature. But if you heat it, then the water's going to come out. And around about 400, it could do a lot of damage because of the nanoporosity. There's a thing called the Young and Laplace equation, which says delta P equals 2 cos theta over R. R is in the bottom. R is 10 to the minus 9. So that means R is the delta P is plus 10 to the minus 9. So you've got huge forces in a nanotunnel. And that water going in or water going out is going to crack it. You take a pure geopolymer made as nice as you can with metakaolin and the works, you get a bowl of water, you put the geopolymer in, and it goes snap, crackle, pop, like Kellogg's cornflakes. That's all the water going in or the water coming out. So reality week is you've got to make composite. You've got to put in some reinforcements to hold it together. Don't let it break during the dehydration. Okay, so this dehydration and chunks of it will crack it, and so therefore we embarked on a whole bunch of adding reinforcements and what sort of microstructure and what sort of mechanical properties do you get. So you can add particulate reinforcements like charmotte, which is calcined clay to produce mullite particles plus silica. That's the mullite particulates, granite, dolomite, sand, whatever. you can put it, that's particulars, like zero-dimensional defects. Chopped fibres, alumina fibres, basalt fibres, carbon fibres, alumina platelets from grinding media, fabrics, you know, and there's long fibres, and then fabrics, carbon fibre, NASA, Nextel 610 alumina 720. Basalt weaves. The basalt fibres from Technobasalt in Kiev, and also Kamenny Vek, Moscow. They produce good basalt fibres, 1200 C capability, and these can be used as a cheap but pretty good reinforcement compared with the expensive 3M Nextel fibres. I've got some mullite, single crystal fibres from Moscow with love. And then, well, since you make geopolymer at room temperature, you can put in polymeric fibres because they can't take the heat, and then a whole bunch of biological fibres. Just a quick little look at it. Here's alumina platelets. Microgrit is a company that sells alumina platelets, roughly 50 microns in diameter. You throw them into, this was potassium geopolymer, and you get 30 or 50 or 70. Usually you can only get about 15 weight%, but if you vibrate the hell out of it, you can get up to 50 weight%, which is 70 weight%, which is 50 volume%. And then you make that composite and you heat it, 300, 600, 900, 1200, and you measure the mechanical properties. The strength is pretty good, 20 megapascals up to 1200 degrees C, and high strength concrete is 7 megapascals down here somewhere. So that might be useful for something. If you break this at room temperature, you get this roughly 20. But if you break it in situ in the instron at high temperature, you can get 40 megapascals up to 1200 degrees C, which is a good high temperature composite, you know, and it doesn't cost much. Here you can throw in basalt, chopped fibres, a 1/4 inch or a 1/2 inch. You can get 17 megapascals or 27 megapascals just with 10 weight% basalt chopped fibres. This was a vertical lift-off runway. The Air Force at Tyndall Air Force Base north of Cuba wanted, now the aeroplanes don't just run off like that, they take off like a rocket and then they go somewhere. That's called a vertical lift-off, and when they take off they burn the cement and little rocks hit the aeroplane. And Edwards Air Force Base in California, as soon as one of them take off, you have to go out and vacuum the air, the thing to clean up the little rocks. Well, when you put, this was cesium, nothing happens to 15, well here, a bit of water, a glassy phase comes out, but 1500 C, 5 minutes with oxyacetylene torch, nothing happens. Part of that was because the thermal expansion of cesium is approximately 0. So here's just a bit of a summary. Those particulates, the chopped fibres, and the weaves. The weaves have the best mechanical properties. The tensile strength. The best thing NASA uses now is Nextel 610 monazite. Coated alumina fibres, and their tensile strength 117 at about 10 times the price. But if you use Nextel 610 plus geopolymer, then you can get just as good, if not better. And if you use cheapo basalt, then it's well, it depends on the basalt. But the flexural strength with basalt is quite respectable. 41 megapascals compared to 40 for mullite and 50 for alumina. So now this talk is supposed to be about processing, about geopolymers and high temperature materials. So 2 ways to do that. One is make composites that go to high temperature, like I just talked to you about. The other one is use geopolymers as a processing route, an alternative way to make ceramics. There's a phase diagram. Sodium, aluminosilicate, and the 1,1, that's weight percent, this is mole percent, I think. The 114 compound is here. That's the geopolymer composition. But to make sodium into a ceramic, you don't get 114, you get 112. That's called naphthalene. 114 is jade, the toughest mineral. But you need geological pressures, 1.7 gigapascals, 1250 C to make jade. But that means that's a synthetic way to make jade, you know, if you've got some friends in the geology department. To make lucite, the 114 with potassium is lucite, and that's has got intermediate thermal expansion used in the dental industry. The thermal expansion of sodium, naphthalene, is 50 by 10 to the minus 6. Potassium is 15 to 31 by 10 to the minus 6. And cesium, it's around about 0.45 to 1 by 10 to the minus 6. Cesium produces lucite at 1100 C. Lucite is very creep resistant. There's YAG, mullite, lucite, hexacalcium. It's very creep resistant, and it melts about 1940 C. So that's good to know. So thermal expansions, sodium GP 50 by 10 to the minus 6. That's big long silica chains flop around a tiny little sodium atom. The chains can do what they like, so they stretch 50 by 10 to the minus 6. Potassium is a bigger cation, so the chains can flop around to some extent, but their thermal expansion is only 26, 28. Cesium is a big fat cation. The sodiums are trying really hard to get around it. So there's a very little thermal expansion, 0.45 by 10 to the minus 6. So now, if you can start tailoring the thermal expansion. Make a geopolymer coating on a metal, figure out what the metal thermal expansion is, whip up a mixture with a similar thermal expansion, and they'll all expand together, see? So, yeah, we're working on that too. It works. So, now that's like heating a ceramic to make heating a geopolymer to make a ceramic. Here is heating a geopolymer to make a ceramic powder, and this is called carbothermal reduction and carbothermal nitridization, and it's a way to make ceramics cheaper. So I teach ceramics how to make silicon carbide. You Aitchison process. You go down to the Bordensee and you get a hydroelectric power that costs a fortune, and you get silica and coke and grind and grind and grind, and then you heat for 2,500 degrees C for days, and you make silicon carbide, and then you grind and grind and grind and grind and get some silicon carbide to sell. That's a lot of energy, lot of energy, lot of energy. Meanwhile, the trick is geopolymer makes nanoparticulates, right? Well, go with the flow. If you have a nanoparticle, the diffusion distance is very short, small. So you get some geopolymers and you grind it. It's not as hard as silicon carbide. And then you put it in flowing argon or nitrogen. We did 1400, 1500, 1600. And 1 or 2 hours, and you get nano, silicon carbide, silicon nitride, or silicon. These are high-tech ceramics. And so the reason you can do that is these little nano precipitates, so diffusion distance is short. When you heat a ceramic, a geopolymer, it'll convert to a ceramic at a crystalline material at 1,000. Even though it's microstructure, it's still nano. So can we use these techniques already established in minerals processing, can we convert a geopolymer to its carbide and nitride analogues by carbothermal reduction? use carbon for reduction, use heat for diffusion, and if it's flowing, the aluminum melts to 600. It goes away with the gas. The CO2, some CO2 goes, and what's left is the refractory part. So this study investigated silicon carbide. If you want to do nitridization, instead of argon gas, it's nitrogen gas. And what you do is you get metakaolin and you mix it with carbon. You can use sodium, potassium or cesium. We did the whole systematic suite. So first you make the geopolymer, then you grind it up and mix it with carbon. Yeah, make it, but you could, this worked, and you mix it with carbon, and then you do 14, 15, 1600 under argon or under nitrogen and analyse it. If it's argon, then it's carbothermal reduction. If it's under nitrogen, it's carbothermal reduction and nitridization. That means nitride's formed. His whole, do X-rays and Rietveld, and Rietveld tells you how much of each phase you got. 80% of this, 20% of that. So 1400 C you get alumina and silicon carbide. 1500 C more silicon carbide, just little alumina. 1600 C silicon carbide, about 97%. Now, if you were to make alumina silicon carbide composites, you'd take this and hot press it, But here you can make just about pure silicon carbide just at this low temperature. And the SEM shows that it's nano soft agglomerates, that's sodium. In the TEM, it looks like nanoparticles and sometimes needles, whiskers. Silicon carbide nanoparticles. So we did a lot of TEM, and basically this sort of summarises this little part of it. If you take silicon 14, 15, 1600 with sodium GP, potassium GP or cesium GP, and for 2 hours you could get like 97% of silicon carbide, or you could get a mixture, silicon carbide alumina. Or if you use potassium GP, you get 100% alumina, that expensive way to make alumina. But it's just an academic, good to know. Next thing is treat it with nitrogen. This is the carbothermal nitridization. So here, if you take nitrogen with sodium geopolymer, ground it up, add carbon, 18 moles of carbon, excess carbon, to produce the reducing atmosphere. Heat it between 14 and 1600 C, as 14, 15, 16 in nitrogen. Then you'll get alpha silicon nitride and beta silicon nitride, some alumina and some aluminum nitride. So you get mostly alpha and beta, 1500 alpha and beta, 1600 more beta and less alpha. And so there's SEM. The beta are the needles. We deliberately put in beta silicon nitride into alpha silicon nitride as a crack deflection toughening mechanism. But this has got 50-50, so it's even more useful. And here's more rigorous, detailed TEM to prove that, alpha and beta. This is potassium, similar results. And TEM says, yeah, you make alpha silicon nitride and beta silicon nitride, and more detailed TEM to prove it. So this is a bit of a summary here about you add carbon, but you do it in nitrogen. Here's the nitrogen and you add carbon. You do 14, 15, 16 with sodium, 14, 15, 16 with potassium, 14, 15, 16 with cesium for 2 hours. And so here you'd form, this says you'd form alpha silicon nitride and beta less, and a bit of aluminum nitride. Here with potassium, you always make the predominant phase is beta silicon nitride, and here with cesium, you'd make alpha silicon nitride. So that's good to know. Then the other one is, if you don't add so much carbon, just 9 moles of carbon, then you don't take away all the oxygen. Carbon plus oxygen equals CO2. Just put 9 moles, and then you start forming sialons, which is a pretty good high-temperature structural ceramic. It's already nano for you. You don't have to grind it. You just have to make it flow out, flow the the gas over it, and then collect it. If you sialon, even 1400 C with sodium, cheap, you just form sialon there. Or 1500 C, sialon, or 1600 C, sialon and some alumina. So these are ready-made composites. All you've got to do is press them and fire them, and so they're already little, 10 microns or they're soft agglomerates by now, or even hard agglomerates if you do it for a long time, but they're still less than 10 microns. So here the silons, you can always make a lot of silons at 1500 C, that all make silons. So, in conclusion, this is the part where you wake up. The carbothermal reduction or nitridization of geopolymers. Higher levels, over 95% of silicon carbide was synthesized from sodium precursor using 18 moles of carbon, plenty of excess carbon to take away the oxygen. Carbothermal reduction, silicon carbide, alpha and beta silicon nitride and sialon ceramics could be cost effectively synthesized from geopolymer precursors. Sodium geopolymer have an advantage over potassium and cesium in its low cost. By focusing on the sodium and potassium, you can get useful structural ceramic and ceramic powders to make components by an inexpensive geopolymer route. And so, summary, what we talked about, what are geopolymer starting materials? Microstructure, nanoporous, nanoparticulate. You can make tailorable thermal expansion oxides, you can make non-oxides. There's a bunch of potential applications, and there's these two, every year, this next year is the 18th annual announced symposium on geopolymers, and it's produced in conference proceedings, so there are 17 books published by the American Ceramic Society, and any papers coming here are also very welcome. And also there'll be the ECI, Engineering Conference International in Portugal next year is starting up. That's got a mixed community, alkali activated materials and geopolymers, but we're still trying to get them to wash out their mouth when they use the geopolymers the wrong way. So thank you very much.